In this video, we're going to discuss the concepts of absolute and conditional convergence and look at some examples of each. We're going to focus our attention on series that have both positive terms and negative terms. This includes alternating series, where we have the signs of the terms alternating between positive and negative, as well as any other series that has both positive and negative terms. For example, we could have series where the first two terms are positive, the next two terms being negative, the next two terms positive, and so on. It turns out that for such a series, one with both positive and negative terms, that there are actually two different ways in which the series could converge. In order to illustrate these two types of convergences, we're going to consider the following two alternating series. First, we have the series from n equal 1 to infinity of negative 1 to the n over n squared, and also the series from n equal 1 to infinity of negative 1 to the n over the square root of n. Both of these series are easily shown to converge by the alternating series test. However, the alternating sign is necessary for one of these series to converge and not necessary for the other one to converge, as we'll see now. If we take the series of absolute values that correspond to the series negative 1 to the n over n squared, in other words, we take the absolute value of each term of our series, we'll get the series from n equal 1 to infinity of 1 over n squared, since the absolute value will remove the alternating sign given by the negative 1 to the n in the numerator. We know the series from n equal 1 to infinity of 1 over n squared is a convergent p-series, since here the p-value is 2 and that is greater than 1, and therefore this series of absolute values will converge. This means that our series here that we were considering, negative 1 to the n over n squared, actually would converge without having an alternating sign, which means that the alternating sign is not necessary for the series to converge. It would converge with or without the alternating sign. On the other hand, for the series negative 1 to the n over the square root of n, if we do something similar and take the series of absolute values, we get the sum from n equal 1 to infinity of 1 over the square root of n. Since the square root of n is equal to n to the 1/2 power, this is a p-series that diverges by the p-test, since here the p-value is 1/2 and 1/2 is less than 1. And so here we have a series that converges by the alternating series test, but if we took away the alternating sign, the series diverges. And therefore, the alternating sign in this particular series is necessary for convergence, as opposed to negative 1 to the n over n squared, where the series would have converged even without the alternating sign. And so here we have these two different types of convergences for these alternating series, one where the convergence would have still held even without the alternating sign, and another where the alternating sign is necessary for convergence. We give these two different types of convergences names. First, we say that the series n equal 1 to infinity of a sub n absolutely converges, or converges absolutely, if the series of absolute values, the series from n equal 1 to infinity of the absolute value of a sub n, converges. This means that our series will converge without the alternating sign. This is what the absolute value is taking care of. It's getting rid of the alternating sign and making all of the signs positive. And so an example like the series negative 1 to the n over n squared, where we can get rid of the alternating sign, resulting in a series that still converges. That is an example of an absolutely convergent series. It's one where when we take absolute values of each term, in other words, getting rid of any kind of negative signs in front of any of the terms, then the resulting series will converge. The second type of convergence is called conditional convergence. And here we say that the series from n equal 1 to infinity of a sub n conditionally converges, or converges conditionally, if the series of absolute values diverges and the original series with just the term a sub n converges. This is just another way of saying that our alternating signs, or more generally, our negative signs in our series, that these are actually necessary for the convergence. If we get rid of them, in other words, if we take the absolute value of each term, we will get a series that diverges. But if we don't take the absolute value, if we leave our series as is, we actually have a convergent series. And this indicates that the alternating signs are necessary for that convergence. We saw this behavior in the series from n equal 1 to infinity of -1 to the n over the square root of n. In this case, that series converged by the alternating series test, but if we took the absolute value of the terms, we ended up with the series of 1 over square root n, and we know from the p-test that that series will diverge. So to summarize the two examples that we've seen, the series from n equal 1 to infinity of -1 to the n over n squared is an absolutely convergent series, since when we take the series of absolute values, we obtain the series with term 1 over n squared, and that is a convergent p-series, and therefore the series of absolute values converge, and therefore the series is absolutely convergent. On the other hand, the series from n equal 1 to infinity of -1 to the n over the square root of n is a conditionally convergent series. To see this, we note that the series of absolute values becomes the series from n equal 1 to infinity of 1 over the square root of n, which we know diverges by the p-test. Here p is 1/2, which is less than 1. And not only does the series of absolute values diverge, but the original series with the alternating sign converges by the alternating series test. And so these two facts together tell us that our given series conditionally converges. There's one often confusing aspect of the definition of absolute convergence that we should address quickly. Part of the definition for conditional convergence requires that the given series converge, which would make sense. If we want something to converge conditionally, we certainly want it to converge. However, the definition for absolute convergence does not require the series to converge, and that part is omitted for a very specific reason. It's because that if a series absolutely converges, meaning if the series of absolute values converge, then the given series must converge automatically. And so there's no need to add that as part of the definition of absolute convergence, since whenever we have a series of absolute values converging, the given series will automatically converge. And so there's no need to actually check whether or not an absolutely convergent series converges or not, because it will automatically. For this reason, it's advantageous to always check a series for absolute convergence first. If we have a series and we'd like to determine if it absolutely converges, conditionally converges, or diverges, we can check the series of absolute values first. If this series converges, then we know our given series absolutely converges and we're done. If the series of absolute values diverges, then we can use the alternating series test or some other test to check for conditional convergence, in other words, to see if the given series converges. And if it does, then we have a conditionally convergent series. And if the given series diverges, then that will be the conclusion that we draw for our problem. So let's take a look at a couple examples, in which case we will always check for absolute convergence first. So here we want to determine whether the series from n equal 1 to infinity of -1 to the n plus first power over 3n plus 1 converges absolutely, converges conditionally, or diverges. We're first going to check to see whether the series absolutely converges. In order to do that, we need to find the series of absolute values and analyze it. In this case, when we take the absolute value of -1 to the n plus 1 over 3n plus 1, the absolute value neutralizes the alternating sum, the -1 to the n plus 1, and we're left with the series with term 1 over 3n plus 1. And now we have a series with positive terms, and we have an array of tests that we can apply to this particular series. In this case, we notice that this series term 1 over 3n plus 1 looks a lot like 1/3 times 1 over n, or 1 over 3n. And so here we're going to use the limit comparison test to compare our series with the divergent p series 1/3 times 1 over n. And so to use the limit comparison test, we're going to take the limit as n goes to infinity of the sequence or the series term that we are looking at, the 1 over 3n plus 1, and we're going to divide that by the series term we're going to compare it to, which is 1 over n. You could also use 1/3 times 1 over n here, but 1 over n is a bit simpler. So here we're going to take the limit as n approaches infinity of n over 3n plus 1. Once we, instead of dividing by 1 over n, we'll multiply by n, and we end up with this. We can use L'Hopital's rule here and see that we're going to get 1/3 as our limiting value. You could also multiply and divide by 1 over n, and then evaluate the limit here. But here we can take the limit, we can use L'Hopital's rule to get the limit of 1 over 3, which of course is just 1/3. And so here we get a number, a numerical value, a finite number that is not 0. And that tells us that the two series that we are comparing using this limit both converge or both diverge. And of course we know the sum from n equal 1 to infinity of 1 over n diverges. This is a standard p series, so this diverges by the p-test with p equal to 1. And whenever p is equal to 1, we know that our series will diverge, and therefore our given series also diverges. So our series with term 1 over 3n plus 1 will diverge by the limit comparison test. And this was justified. Below, we computed this limit, getting 1/3, and therefore both series have the same behavior. And so we know the series of absolute values diverges, and therefore we know that our given series does not absolutely converge. Converging absolutely would mean that the series of absolute values converges, and here we've just shown that it diverges. So by doing this calculation, we've eliminated one of the 3 possibilities for this particular series. We're now going to check to see if the series conditionally converges. And in order to do that, since we already have the series of absolute values diverging, we simply need to know that the given sequence as written converges. Since it's an alternating series, we're going to use the alternating series test to check for this. To check for conditional convergence, we let b sub n be the non-negative part of our series, so that would be 1 over 3n plus 1 here. For n to be a positive number, we know this will always be positive, so that first condition will hold pretty trivially. The second condition is we want the terms to be decreasing, and so we want to compare 1 over 3n plus 1 with 1 over 3n plus 1. So we want to compare the given term with the given term with n plus 1 substituted in. And of course, this will amount to 1 over 3n plus 4 and 1 over 3n plus 1. And certainly 3n plus 4 is larger, so the denominator there is larger, and so we have a smaller value. And so we have decreasing terms. And last but not least, we have the limit as n goes to infinity of 1 over 3n plus 1. And here, the denominator will get large, and so we have 1 over very, very large numbers as n increases, and so we get a limiting value of 0. And here we have all 3 of our conditions checking out. So our given series converges by the alternating series test, and therefore, since the absolute value series did not converge, it diverged, our series conditionally converges by the alternating series test. Right? Again, this means that when we take the absolute value of our series, we have a divergent series, but the series itself converges. And so, in other words, the alternating sign is necessary for this particular series to converge. Without it, it diverges. In this example, we want to determine whether the series from n equal 1 to infinity of negative 1 to the n times n over n to the fourth plus 1 converges absolutely, converges conditionally, or diverges. As with any of these examples, we're going to first check for absolute convergence. And this means we want to take the series of absolute values of the corresponding terms. So here we want to take the absolute value of negative 1 to the n times n over n to the fourth plus 1. The absolute value neutralizes the alternating sign, and so we're simply left with the series from n equal 1 to infinity of n over n to the fourth plus 1. And this is a series with positive terms, and so we can use any of the various tests that we have for series with positive terms. This series looks a lot like n over n to the fourth by ignoring that plus 1, and that would be 1 over n cubed. And we know that is a convergent p-series. And here we can actually use a comparison. We could also use the limit comparison test if we wished. But here a standard comparison would work fine. N over n to the fourth plus 1 will be less than or equal to n over n to the fourth, because plus 1 will make that denominator larger and therefore the entire expression smaller. And n over n to the fourth is the same as 1 over n cubed. And we know that this series, n equal 1 to infinity of 1 over n cubed, we know this is a convergent series. This is a convergent p-series. So this converges by the p-test. And here we know that since p is equal to 3, and that is greater than 1, that this series will converge. This is a convergent p-series. And therefore, our series of absolute values is going to converge, again, by the comparison test here. Here we have a series, and the terms are less than or equal to the terms of a convergent series, and this is exactly what the comparison test says, is that when this happens, our given series will converge. And so here we have the series of absolute values converging, and so our given series converges absolutely. Since this means that the series converges automatically, we don't need to apply the alternating series test here, although we certainly could if we wanted to, but knowing that the series absolutely converges is sufficient to conclude that it does converge itself, but also that in absolute value, it also converges. If you'd like to try a similar example, you can pause the video and determine whether the following series converge absolutely, converge conditionally, or diverge. You can resume the video in a few seconds to see the completed solutions. Here we have the series from n equal 1 to infinity of negative 1 to the n plus 1 times n over 2n cubed plus 1, and the series from n equal 1 to infinity of negative 1 to the n 3n squared all over the square root of n to the fifth. For the first series, we have the series of absolute values being the series from n equal 1 to infinity of n over 2n cubed plus 1. This term is less than 1/2 times 1 over n squared, and the series with term 1/2 times 1 over n squared is a convergent p-series, since the p-value here is 2 and 2 is greater than 1. Therefore, our series of absolute values can be determined to converge by using the comparison test, comparing it to this convergent p-series, and therefore our given series absolutely converges. For the second series, we take the series of absolute values, which gives us the sum from n equal 1 to infinity of 3n squared over n to the 5/2, which we can simplify as the sum from n equal 1 to infinity of 3 over n to the 1/2. This is 3 times a p-series with p-value of 1/2, which is less than 1, and therefore this series diverges. Since the series of absolute values diverges, we know the series does not absolutely converge. We then move on to try the alternating series test. Here, b sub n will be the non-negative part of that series, the 3n squared over the square root of n to the fifth, which, as we've simplified above, is equal to 3 over the square root of n, or 3 over n to the 1/2. This expression is always positive when n is positive. We know that 3 over square root of n plus 1 is less than the 3 over the square root of n, because the square root of n plus 1 is a larger denominator than the square root of n, and so our terms are decreasing. And the limit as n approaches infinity of 3 over the square root of n is also equal to 0. And so the alternating series test properties all hold here, and therefore our given series is known to converge by the alternating series test. And since we have the series of absolute values not converging and the series itself converging, these two facts imply that our given series conditionally converges.